So another Friday late in the semester. Thanks for coming. For today, I'll continue along talking about LEDs and then get into lasers. Just to sort of set the stage again, remind you where we've been and where I'm heading, I guess. The first form of light we encountered and paid much attention to was thermal light emitted by a hot surface, namely the sun, and the quantum effects in that are minimal. I mean, they're actually there in the spectrum, but not so. As you notice, in light from discharge lamps, where you're now looking at the emission of atoms, or in the case of fluorescent lamps, you're looking at the emission only from phosphor powder. Now quantum stuff really shows up. The fact that certainly in an atom, the structure of the atom is all determined by quantum mechanics, quantum physics. The orbitals in which the electrons live, or it can live, are very much constrained by the fact that they're waves. Literally in an atom, the electrons are focused on that positively charged nucleus, which keeps them attached. But they live as waves around the nucleus. They also interact with one another because they repel each other. So the structure of an atom is determined. It's fairly complicated, but at this point very well understood structure, with all those electrons trying to stay away from each other and get as close as they can to the positively charged nucleus, and yet they have to be waves. Two electrons per wave, according to this Pauli exclusion principle. It forbids identical electrons from being in the same wave. Anyway, it gives the structure to the atom and its orbitals, and the spacing in energy between those orbitals is responsible for the emission spectra that we see in the discharge lamps. You put neon in, you're seeing specific frequencies and correspondingly wavelengths of light occurring because there's a pair of orbitals separated by the right amount of energy to produce that light. If there's no pair of orbitals that is separated by the right spacing, you don't get that light out of the neon. In the phosphors, which are powders, so they're little crystals, the quantum structure is a little more complicated. It's still quantum waves there, and the electrons are still going from one quantum wave to another in the process of emitting light. And that's going to be closely related to what I'll talk about today in looking at light-emitting diodes. So the light from discharge lamps has a lot of quantum physics in it. And as we'll see, the light from light-emitting diodes also has a lot of quantum physics in it. So the story of light-emitting diodes starts with just diodes, which are one-way devices for electrons. In fact, for electrons. If you zoom away from the fact that it's electrons moving through the diode, you can just simply say it's a one-way device for current. But we do have to pay attention to the electrons in this case. And just to get started, since we're talking about how electrons move through solids, we'll start basically simple and work our way up. And so my first question to look at is why can't electrons move through insulators? So glass, crystal of quartz, salt crystal. You can't get electrons. Basically, they don't carry charge. It doesn't move through them. It's got electrons in them. Why don't they move? Why can't they make the shift? And it turns out it's all about quantum mechanics, and that where the electrons live, they're once again living in these quantum standing waves within the solid. And those waves are arranged in this case such that nobody can move, as we'll see. And the result is you put an electric field across, say, a salt crystal. You put positive charge on one side, negative charge on the other side of the crystal, create an electric field that points from the positive side to the negative side, and that pushes on all the electrons. They all want to go opposite the field because they're negatively charged, but they can't move. So why not? And the story has to do, finally, with the nature of the quantum levels, or the quantum waves that are possible in a solid. So this is a schematic. This is the drawing that I used prior to the current drawings in the book, in the electronic book, are videos. So I encourage you to watch them. I could cut the videos out and try to play them for you, but I feel kind of cheesy doing that, like sort of presenting the class rather than giving it. But do go watch them, because the animations finally, I was able to illustrate things that I could talk about in class, but I can't show you quite as well. Anyhow, if you think about building an atom, so let's zoom back to, go rewind to talk about an atom. When you build an atom, you've got this positively charged nucleus, and you start to bring in the electrons. The first electron tends to settle in the lowest possible energy, the lowest energy orbital. That is, it's a standing wave, or that's the reason for the word orbital instead of orbit. It goes in the lowest energy one. It's happy there. It's very tightly, it's in close to the nucleus, so it's close to the positive charge. It has a relatively smooth wave function, not a lot of sharp edges to it, and that corresponds to low kinetic energy, it turns out. So it's low in energy in every way. Second electron comes in. Say we're building neon. Second electron comes in. It can join the first electron in that lowest orbital, except it has to be sure that its spin, the only thing that distinguishes it from the electrons already there, its spin has to be opposite. So now you've got two electrons in that orbital, one spin up and one spin down. That orbital's full. You can't put any more electrons in. You bring in a third electron, it has to go in the next higher energy orbital. It's then joined by a second electron, which also goes in spin opposite, and so on. You work your way up. By the time you've got 10 electrons in this neon atom, you have used 5 orbitals. You've got 5 pairs of electron, one spin up, one spin down. They're all snug in as tight as they can get towards that nucleus. They'd love to get closer, but they can't because of the Pauli exclusion principle, preventing them from glomming onto from joining up the same orbital. And it's happy. It's a neon atom. All right? Suppose you build a solid instead. Well, if you're building a solid, we imagine a solid in which we've got a whole array of positively charged nuclei, and we'll pick semi-arbitrarily. Let's make the solid all silicon atoms. Silicon being the classic, it's the classic semiconductor. Do I want to use silicon? Yeah, it's okay. So we'll take a piece of silicon. Not silicone, which I work on, silicon. The distinction between those two, just in case you ever wondered, silicon is the element. Silicone is a plastic, a polymer, that has at its heart silicon, but it's got oxygen and carbon and hydrogen. It's more complicated. All right, so silicon. Suppose we're assembling silicon. Start out with no electrons. We just put all the silicon atoms out there. They'll go into a crystalline array. Crystals are very orderly arrays of atoms. There are many different arrangements you can have, but basically, if you know where the atoms are in one small patch of a crystal, you can predict where all the other ones are, because they're all evenly along lines or boxes or tilted boxes, all sorts of shapes that are possible in nature, but they're all neatly arranged, like when you go to the grocery store and they've got a beautiful display of apples or oranges, all carefully stacked. I mean, that's what the nuclei and they're ultimately the atoms in a crystal look like. If you could see that zoom in and see atomic scale stuff. All right, so we've got all the nuclei out there. That can't last. That's too much positive charge. They're going to hate it. So we start bringing in electrons. And where do the electrons go? Well, they go into standing waves of this whole system. And it turns out that the first electrons that come in end up basically focusing their attention on the atomic nuclei individually. And so they recreate the orbitals, and they behave as though they're associated with individual atoms. And so you end up building most of what were a whole bunch of independent atoms. All but the last group of electrons are kind of like they're kind of delegated out to the atoms. It's the last ones that you bring in that, instead of going sort of paying attention exclusively to one atom, they begin to sort of have broader view of things, and they go into standing waves that extend over many atoms. What they see is still positively charged stuff around, and so instead of being completely paying attention to this positive charge, they can spread out more, make a smoother wave function, and therefore have less energy in the wave function itself, and share their attention to many nuclei. So the last electrons that go into quantum standing waves that are sort of the whole solid. not just a little local atom. And those extended standing waves are called levels, just to give them a name. And level, associated with the idea of level, is a level of energy. And here they are, so we're building up. This picture actually is not a picture of silicon, it's just a generic picture. It actually is a metal, as we'll see in a little while. As you build up the electrons, the way I've got this drawing, the concept of the drawing is, vertical is energy, it's not a location in space. Left and right are real, those are locations in space. So this is the left side of the material, this is the right side of the material, and as you go higher up in these little boxes, each box represents a possible standing wave, a possible level in that material. If that possible standing wave actually has an electron doing that standing wave, you see it there. And I labeled them red and blue because one of them spin up, one of them spin down, and having arrows or something like that is just too much of a nuisance. So I don't know which one's which. Blue might be spin up and red is spin down. It doesn't matter. So as you construct the solid and put all the electrons in, you ultimately begin putting electrons into these levels, these standing waves that are possible within the solid, and you fill up those levels from lowest energy to less low energy to somewhat higher energy and so on until you run out of electrons. You run out of electrons when you hit neutrality, when basically you have put in one electron for every positive proton there is in the solid. At that point, we're done. You've made an electrically neutral solid, and it has characteristics, it turns out, that are determined by essentially where did you run out of electrons? What are the levels like in the vicinity of the last electron you put in? Are there more levels, which is to say more standing waves, at about the same energy as the last electron you put in, or not? Or did you put in the last electron in the process of filling a group of levels, what is known as a band, and the next electron, were you to want to put one in, would it have to go into a level with a much higher energy? So what's drawn here is a material in which, in principle, we have put in enough electrons to make it electrically neutral, and in the process, we did a couple things. We filled this band of levels. Now, what's a band of levels? These levels all originated, these standing waves all originated typically in some orbital of the atoms from which this material was made. So when you bring together a whole bunch of silicon atoms, the orbitals that were present in a silicon atom don't completely disappear. They mix and stir with the orbitals from the other silicon atoms, and they create groupings. And so if you look at the ancestry of these levels, they all share a common ancestry that has to do with some orbital structure within the silicon atom. And consequently, they all have relatively similar energies. They're structurally a little different. Each one is its own little wave. There's something a little different about this one than that one, and so on. And they have a little bit different energies, but not a huge difference in energy, so that you can kind of think of them all as a group. And they're called a band. You've encountered this in chemistry somewhere or other, talking about in atoms, that the orbitals also group up. There are typically a bunch of orbitals that share pretty similar energies, and you talk about them as a shell of orbitals. And filling those all, there's a lot of similarities. And then when you run out, after filling a shell, and if you make an atom that needs another electron, it has to go in a much higher energy orbital, and that really affects the chemistry of the atom. Anyhow, so this band has been well filled, all the electrons. It has as many electrons as it can hold, according to the Pauli exclusion principle. There are 2 in every standing wave. All the standing waves have an electron doing them, or pair of electrons doing them. We're done. That grouping is done. The band's done. And to continue towards electrical neutrality, we had to add more electrons, and we began to fill this band. But we didn't fill the whole thing because we ran out of electrons. We hit electrical neutrality before filling the band. So there are electrons in all these standing waves that are marked, but the standing waves that are unmarked are negligibly different in energy. They just don't have an electron doing them. And with almost no effort or energy, this red electron, for example, could go over and do this standing wave instead of that standing wave. They're almost equivalent. Who cares? And the result of this is this material has a behavior when you put an electric field on it that's different than a material in which all these levels in this band are filled. One is an insulator and one is a conductor. Yeah, John. What about a semiconductor? Silicon actually is technically a semiconductor. An insulator and a semiconductor have almost no difference, except a semiconductor is a poor insulator. What's poor about it? It means that with not too much energy, as we'll see, you can get an electron freed up to move. An insulator is normally thought of as something that's really tough to get the electrons to move. And without enormous inputs of energy, they're stuck. Semiconductor, with small inputs of energy, they can become mobile. And often the definition of what's small amount of energy? Thermal energy. So at room temperature, for example, many semiconductors will begin to conduct a little bit of electricity because just thermal agitation. This is a conductor. It's true that all the electrons are paired, but this level over here, which is a quantum wave very similar to the quantum wave this electron lives in, that electron could transition from this level to that level almost for free. Thermal energy certainly would make it move, could make it move. So this is easily allows electrons to shift around and respond, for example, to electric fields. So my analogy in the book and just in general, this resembles a theater. Forget this. This may be the orchestra pit. It's all full. This is the ground floor of a theater in which the people are sparsely placed. Shades of today. If I told you all to shift towards the west, you could all by tiny movements. You're not allowed to just like jump out of your seat and fly across the room. You have to go from seat to seat. You all could shift towards the west. You know, people have to move and move. You could all sort of gradually one seat at a time. You could work your way across the room, right? If the room were completely full, however, that process of moving would be hugely impeded. The only thing that could possibly happen is that people at the very end can move out, and then you move one person at a time. It's not going to happen if the thing's big enough. There's almost no movement. So this is a partially filled theater, ground floor. Everybody can move in response to some push. All right? Oops, went too far. So metals. So this is, as I said, what I just described for you previously was a metal. The Fermi level, it was on the previous slide, but I'll just say, the Fermi level is just conceptually the last level filled, or the next level, or I guess it's halfway between the last level that was filled to reach neutrality and the next level that would be filled if you needed one more electron. It's a level in energy. So it's not actually, it's a hypothetical thing. It's just what energy would you need to put in one more electron? So if the Fermi level occurs in the middle of a band of levels, then you've got a metal. The reason for that is, you know, you've got lots of levels that are filled, lots of levels that are empty. They're all very close in energy. And in the presence of an electric field imposed by, say, a battery from outside, you put electric field into this material, they're going to start moving. So the electrons will begin to move opposite the direction of the electric field, again, because they're negatively charged and contrary. So this hopping motion is schematic for what happens. It's like you take the theater and you tilt one side high and one side low. That's what the electric field does, and people begin to sort of migrate downhill across all the seats. All right? Conductivity. So this is what is present in any metal you encounter. You go look at it, you'll find that the last electrons will have partially fill the band. There are other levels very much nearby. With almost no effort, the electrons can shift from one level to the other and begin to wander through it. All right? What's the alternative? The alternative is an insulator, of which semiconductors are part. So semiconductors are a special, again, they belong to the insulator class. The electrons needed to complete the solid completely fill a band, and then you run out of electrons. No more needed. The result is you have all these electrons in the levels, filling every last one of them. They're filled in the sense that no more electrons can be in any of those levels without violating the Pauli exclusion principle, which is part of nature. I mean, you can't violate it. It's not like you can violate it and then get arrested. You just can't violate it. And so there they are. And if you apply an electric field by putting positive charge on one side, negative on the other with a battery, creating the electric field's there, the electrons are all pushed in this picture toward the left, but they can't move. They can't move because they're in a quantum standing wave and there are no other quantum standing waves available that have anywhere near the same energy. And there's no way they can evolve from one wave to the other and move. They're stuck. So that's an insulator. Yeah. This is a drawing of, if you got a semiconductor, how do charges move in a semiconductor? So it's an insulator with a small gap. What is a gap? This band of levels, so some of this is jargon. Levels is a piece of jargon. It refers to the standing waves in a solid. Band is jargon referring to a group of levels sharing the same energy. And actually more deeply, it shares the same ancestry in the atomic orbitals from which the solid was built. Band gap is the energy difference between the highest energy orbital in one band and the lowest energy, not orbital, excuse me, highest energy level in one band and the lowest energy level in another band. Those bands have names. In this case, where for an insulator, again, of which semiconductor is a type, the highest occupied band, that is the band with the most energy and that also has electrons in it, is known as the valence band. Valence is a word inherited from atomic structure. If you remember, the valence orbitals in an atom are the outermost, highest energy electrons in an atom, and therefore the ones involved in chemistry. So the valence band is typically constructed out of those valence electrons in the atoms. And it's typically all full in a semiconductor. In a true semiconductor, it's all full. And the empty band that's available, that is, it's full of levels, it's full of quantum standing waves that electrons could have if they had enough energy. It's available housing, but no one lives there. And it's called the conduction band. So valence band, conduction band. And in a cold insulator, get rid of thermal energy, get rid of everything that would introduce extra energy into the system. In a cold insulator, the valence band's chock full, nobody can move. And the conduction band is totally empty, nobody can move because nobody's there. Apply an electric field, nothing happens. So my theater analogy is the ground floor of the theater is completely packed. The balcony's completely empty, no one's moving. I say everybody head west, no, they don't do it. All right? But, yeah, there it is. In a semiconductor, as opposed to an insulator, in a semiconductor, the gap between these two bands in energy is small enough that thermal energy or light energy can cross it. So in this cartoon, basically, little particles of light. Remember, light's got both a wave character and a particle character. When it's absorbed in a material, the particle character comes to the fore, and pulse of energy, a portion of energy arrives. If the portion of energy associated with one of those quanta of light, one of those photons of light, that's the word photon there, if it's got enough energy to toss one of these electrons from a standing wave in the valence band to a standing wave in the conduction band, the electron can shift. It just changes the structure of its wave. And now you've got a different situation than before. You have some empty, like in this case, one empty spot in the valence band, and you've got one electron in the conduction band. Both of those allow movement. The electron in the conduction band itself can move. It can go from one wave to the next, to the next, to the next, and work its way across my conceptual balcony and come out the side. So electrons can be conducted through the conduction band, but also the valence band becomes conducting as well, because now you've got an empty spot. And when you have an empty spot, you can get this sequence of movements where one electron fills the empty spot and leaves another empty spot, which is filled by another electron, which leaves another empty spot, which is filled by another. So you can get the movement of electrons through the valence band by virtue of its empty spots, which they're talked about by physicists as holes. And the holes move. They move opposite the electron motion. So holes drift towards low voltage. They move in the direction of the electric field, and they imitate positively charged widgets. So they're kind of like positively charged things that percolate their way across the valence band. The long and short of it, though, is that this suddenly becomes a conductor of electricity. And it's made a conductor of electricity by exposure to light. Have we seen that concept before earlier in the semester? Remember zero-graphic copiers? That's how zero-graphic copiers work. That photoconductor drum that they have, that they use in order to move charge around with light so that you can use the image of a document to move, to pick up static, to control static electricity so you pick up toner or you don't. That coating on the drum, the photoconductor coating, is a semiconductor. It's doing this trick. In the dark, it's got a filled valence band, empty conduction band, nothing can move. You can put charge on its surface and the charge will sit there. But expose it to light and you promote some of the valence electrons to the conduction band, and suddenly charge can move. And you can erase static charge on that photoconductor surface. And the rest of the zero-graphic copier follows. Is it okay? All right. Heat also can promote electrons out of the valence band to the conduction band. And as a result of this, semiconductors, which in principle start as completely non-conductors at very low temperature, become increasingly better conductors as they get hotter. That's contrary to the behavior of metals. I showed you the jumping rings stuff. I had that transformer system up here, the AC electromagnet. And I would put aluminum rings, and the aluminum ring would jump up. Remember that guy? And if I put the ring in, this aluminum ring in liquid nitrogen and made it super cold, it became a better conductor and jumped higher. That's generally true of metals. They become better conductors as you cool them down. Semiconductors are the reverse. They become worse conductors as you cool them down. Why? Because the conductivity that they have originates in thermal energy promoting electrons from one band to the other. You get rid of the thermal energy, the electrons all settle down. They fill the valence band, empty the conduction band, nothing moves. So the hotter a semiconductor gets, the better it conducts electricity. Is that okay for everybody? This is why keeping your computer stuff under controlled temperature, keeping the temperature under control is important. You got fans and those gadgets and stuff that kick on. Why don't they want them to get really hot? Well, as they get hotter and hotter, they become better and better conductors, and more current flows, which typically heats them up more and more. So they become better conductors and more current flows, which heats them up more, and you can imagine there's a catastrophe. So computer chips run the risk of overheating and consequently consuming more power and overheating more and then just burning up. So you got to keep them sort of below a threshold at which there's a runaway disaster. All right? This has to be a huge problem for like these giant server farms, the Googles and Facebooks and stuff, and Amazon Web Services, keeping those things cool. Yeah, they use millions of watts of electric power, but they also have to get the heat out of there, because otherwise they will self-destruct. Okay, so next step here is we're heading towards a diode, a one-way device for electrons. We haven't got it yet. We've got devices that will prevent electrons from moving, the insulators, devices that will allow electrons to move either direction, those are the metals, and how about a one-way system? That's tricky. The one-way systems that exist are made, technically they're known as diodes. They're made by tinkering with semiconductors. And the way they tinker with a semiconductor is they introduce what are called dopants. You dope a semiconductor. Chemical impurities deliberately put in to modify the number of electrons needed to reach charge neutrality. If you put in atoms that don't need as many electrons, for example, instead of silicon, which wants, as you know, it should be 14 electrons, right? Yeah, I think it's 14. If you put in a aluminum, which only needs 13 electrons, you end up creating the same crystal pretty much. You don't want to put too much aluminum, just a little. You create a crystal that reaches charge neutrality with slightly fewer electrons, because the aluminum nucleus just doesn't, it's missing one charge. So you end up with a material that's known as a p-type semiconductor for positive charge, for positive, I guess. It's missing a couple of electrons in its valence band. You didn't need them to reach charge neutrality, so they're not there. And the result is the valence band can carry electric current. It's a conductor. Depends on how much aluminum you put in. The more aluminum you put in, the better conductor it becomes. So that's p-type semiconductor. N-type semiconductor you create by adding an extra. You add atoms that have extra electrons that are otherwise very similar to silicon. And what's to silicon's right? Is it phosphorus? I can't remember. Anyway, it might be phosphorus, in which case it's got 5 electrons instead of 4 in its valence. And to reach charge neutrality, you need a couple extra electrons, and they can't go in the valence band, it's full. So they go in the conduction band. So by chemically doping silicon or any other semiconductor, you can deliberately leave some empty spots in the valence band, and that's a p-type semiconductor, or deliberately create some electrons living in the conduction band, and that's an n-type semiconductor. Any questions about these two guys? Now, why would you do that? Well, what if you touch these two together? And let me just go there. Okay, so there they are, sitting side by side. Yeah, John? Which one's a better conductor? In general, the n-types are better conductors because it's the electrons doing the movement. The p-types use this movement of holes, the empty spots, and that's a little bit more awkward. So the n-types are typically better conductors, but it depends on how much dopant you put in. The more dopant you put in, the more either open spaces or filled spaces you got to work with, and the better the conductor gets. And so heavily doped semiconductors are good conductors, and they're used routinely in some of the wiring in computer chips isn't metal. It's heavily doped semiconductor. It's as good as metal. For practical purposes, it becomes as good as metal. Does that make sense? You basically just doctor the semiconductor until it's effectively a metal. Good enough. Okay, so here they are side by side, the P on the left and on the right, and what happens when you touch them? So here they go. We touch. Okay, when you touch the two together, and this is conceptually, they don't actually assemble these guys anymore. They build them much more cleverly than that. In principle, when you touch the two together, the electrons that were sitting in the n-type semiconductor, they used to be sitting up here in the conduction band. I'll go back one. They're there. That pair of electrons, it's got a lot of energy. It's drooling over the opportunity to go and drop into the low energy levels in the p-type semiconductor, but it can't because there's a gap between the two. But when you touch them, oh, they can move, and they do. They drop from one level, from these levels into those, and that empties out the conduction band over a certain region, and it fills the valence band over another region, over the same region, I should say. This region right here, in the middle, where the two materials touch, what's called the p-n junction, is a pure semiconductor again. It has no ability to carry electric current. It's an insulator. So by itself, basically, this is a barrier to the movement of charge across this guy. And that looks like death, like nothing will ever happen again. This is boring, but it's not. It's a weird arrangement where if you put an electric field on it one way, current will flow, and if you put an electric field the other way, no current will flow. So let's try putting the current on one way. So in this case, we have put negative charge on the right side, near the n-type material, and positive charge near the p-type material. And what happens? Well, the electrons that you shove onto the right side can wander into and fill some of the levels in the conduction band, and they can spread out and actually get to the point where they reach the junction, and then at the same time you've been pushing electrons in on the right, you've been pulling them out on the left with positive charge, so the valence band begins to empty out a little bit. So you're filling up the conduction band a bit on the right, emptying the valence on the left, and electrons begin to migrate across the junction because they can, and you get current flowing through the whole thing. Another way of thinking of this is that depletion region goes away. Remember this depletion region here? You can get rid of this depletion region if you shove electrons into it from the right, and if you pull electrons out from the left. So you wipe out the depletion region, and suddenly current flows. What you can't do is push electrons in from the left and pull them out on the right. If you push them in from the left, instead of cleaning up, creating more empty spots here in the valence band, you fill them all in. And if you pull electrons out from the right, instead of making more electrons in the conduction band, you empty it out. So you've done disaster. You've made the depletion region bigger. So you push one direction, you can shrink the depletion region. You push the other way, and you grow the depletion region, the dead spot. Is that followable? So this structure, p-type material on the right, n-type on the left, will allow electrons to move from right to left, but will not allow electrons to move from left to right. If you try to push them backwards, they won't go. You turn the whole junction into a vast wasteland of non-conducting material, and they won't go. All right? So that's a diode. Diodes show up in all kinds of electronic devices. I'm trying to think where they show up the most for you. They show up a lot in the conversion of alternating current from the power line to direct current for your computer gadgets. How do you manage to undo this alternating process? With diodes. It's basically a lot of one-way streets for charge. You could make it so that everybody coming in either of two roads, whether it's this road or that road, they come in with the correct arrangement of one-way streets. You could have them all end up on a certain road, and all coming back a different road. Oh, anyway, so they're used to deal with alternating currents. They're also used, for example, for protection. A lot of your electronics, 20 years ago, blowing out your electronics with static electricity was really easy. We did it all the time. There are endless ways in which you could ruin good electronics. At this point, none of you have probably ever had problems with like your cell phone because of static electricity. A lot of that has to do with protection by diodes, where if charge accumulates where it's not supposed to be, it's shunted off by diodes into a place where it's safe. You put the diode in as opposed to a wire because you don't want to deliberately sort of connect everything electrically so that nothing can have charges on it. Then nothing can work anymore. Anyhow, so diodes, one-way devices. But the story here is not so much about diodes themselves, but light-emitting diodes. Let me blast past these guys. Because there's one. Oh, I don't have a picture of it. Rats. All right, I'll go back to this one, and I'll have to wave my hand. I told you last time that this diode, analogous to this diode, is the idea of two rivers connected by a waterfall. And here's the high river, the low river, the waterfall, right? You can push water in on the high river, have it go down the waterfall and leave through the low river. That works just fine. If you try to do the reverse, which is this other picture, you're now pushing water in on the low waterfall and trying to take it out the high waterfall. It's not going to jump up like that. Not going to happen. Okay? So, going back to this guy. What happens to the energy of these electrons over here as they drift in here, cross the junction, and drop into the lower energy levels of the valence band? Well, in conventional diodes, that just becomes thermal energy. And they try to make it as small as possible so you don't waste too much energy in the process of letting it drop. In light-emitting diodes, that drop occurs in a way that it's kind of creating a high-energy orbital within the material that then can radiate away energy and drop into a low-energy orbital. There actually are sort of atomic-like structures in the semiconductor structure of a light-emitting diode. So that drop emits light. And the efficiencies, they're always working on better and better efficiencies. It's something like 50% these days. So about half the energy you put in the form of, you have to put electrons in at high energy here, take them out at low energy. The missing energy went out as light. Is that okay? Some things to observe. The closer together these two bands are, the less energy is released when an electron drops from the conduction band to the valence band. And therefore, the lower energy the photon that comes out is. So for example, red light. So now I can show you, let's go to, I'll put it up there. Yeah. Side projector, document. Magic. Yay! Okay, we're now looking down at a light emitting diode here, and this will show you the voltage drop across it. So we're going to put electrons in from this side. They're going to go in the conduction band here, drop into the valence band and leave. And this will be the voltage sort of that waterfall. And right now the voltage is 0 and there's no light. As I turn up the voltage, initially there's nothing. I don't have enough energy given to each electron to get it to flow across the conduction band and make the drop. I have to go a little higher in energy, right about there. Okay, where's the light? Okay, so at a little less than 2 volts, a voltage difference between entry and exit, and because electrons are negatively charged, I don't want to talk about which one's voltage plus and minus because it's backwards. Everything is goofy. We're now pushing charges in here. They are dropping down, and in the process of dropping, they are releasing about 1.7 electron volts of energy. The fact that we're measuring the voltage difference across this junction tells us the energy difference. The difference in energy from here to here is 1.7 volts per electron. 1.7 electron volts of energy. It's a little teeny unit of energy I mentioned before. And you need about 1.7 volts to make that jump in order to make a red photon. Because red photons are low energy photons. I said yesterday or last time that it was like 2 volts, 2 electron volts. It's actually about 1.7. All right? If I replace the red LED with a yellow LED, we're still getting it, but barely. Let me go up beyond yellow to green. There we go. Oh, green. Why, you're coming too? Well, let's go to blue. I know for sure. What I'm trying to show you is that you need higher voltage to make the bluer end of the spectrum, and I started with red turned up too high, probably. Now we're at 2 volts. I don't know how the voltage, okay. The voltage went up to 2 volts. I know why it went up. And that's part of the problem. 2 volts is not enough for a blue LED. The blue LED, to synthesize, to create a blue photon, you need more energy. And so the chemistry of the semiconductor in that blue LED is different from that in the red LED. And the gap between these two, the band gap here, right, is bigger. And so it's got to drop farther. You need a bigger voltage to make it work. It needs about 3 volts. There we go. And we don't have a UV one here, but the farther you go into the red end of the blue end of the spectrum, the more voltage you need for the LED. This is why you start needing lithium batteries for the blue and ultraviolet light emitting diodes. They need a lot of voltage because they're producing big, beefy, high energy photons. All right? Time goes by. Returning to my crazy LED system here. This guy, these are lights. I don't know if this is from a street light or from a household illumination system. It's dazzlingly bright, right? It was like $3 on eBay. These must be like the rejects from light companies. These guys run at higher voltage, not because they need more voltage to make the light, but because they put the LEDs in series with each other. So it's like a series of waterfalls, and so you have to have the electrons have to come in at very high energy and work their way through waterfall after waterfall before coming out the other side. And backwards. You know, I should. If I try to run the current backwards, nothing. It's a diode after all, right? I'm trying to put electrons in at low energy, taking a lot of high energy. Not going to happen. Put them at high energy. Ooh. Yeah, that's a lot of light for a very small package. Woo! I like it. Keeps me happy. All right. So those are LEDs. Any questions about LEDs? Lasers is going to have to wait until Monday. All right. Have a good weekend.